All right, hello everyone. So I'm gonna walk you through question 1, A, B, and C. So first, I'm gonna draw the oral dose of what it looks like. Right, so we have an absorption phase and then we have an elimination phase. The elimination phase follows this slope. This is the elimination constant, K, which we've been using all semester. So what we're trying to do is we're trying to find Ka. So in order to do that, we're going to have to first find this linear line and then extrapolate it. So first, in order to find K, we're going to do the same equation that we've been doing all semester, which is ln C2 minus C1, ln C2 equal to ln C1 minus KT. And so we're going to pick 2 points. So as you can see, I have my points over here. We're going to pick towards the end of the slope, so 24 hours and 18 hours. That's going to be ln 1.27 equal to ln 3.88 minus K, and there's 6 hours in between, 6 hours. And so if you solve for that, you're going to get a K of 0.186. Okay, great. That's our first part. Now we want to find up here. We want to figure out what this, the equation for this line is. So in order to do that, we need to find what the y-intercept is. And I'm going to say this y-intercept is equal to A. We're going to use A as our variable. So in order to figure that out, we are going to follow this equation pretty much again. We're going to have ln of our C2, which I'm going to just pick this last point. At 24 hours, we have 1.27 as our concentration. I'm going to set that equal to ln of A, or our y-intercept, minus our newly found K, 0.186, and a time of 24 hours. And so if you do that, you solve, you're going to find that A is equal to 110. So great. That is what our point up here is, 110. Now we're going to, the next thing we have to do in order to find this regression line or residual line is to find a random point. Let's say it's like right here. This is going to be our extrapolated C, or C line. The reason it's extrapolated is because this isn't the actual concentration. As we know, the actual concentration is right here on the curve, but it's extrapolated. It's made up based on this linear line that we found. So once again, we're going to be basically using the same equation. ln C extrapolated is equal to, I'm going to pick my C1 to be our new y-intercept, ln of, I'll write it out first, ln of A minus KT, which is going to be ln C dot, what we're trying to find, equal to ln of 110 minus 0.186 times, I have to choose a time. So here I'm going to pick 0.25. Why am I picking 0.25? Because we have the point. At 0.25, we know it's 51.33. So that's what this time is, 0.25. And we know here is, what did I say? 51.33. And so we can find the time in between the two. First finding what the C dot is. So we're going to get, if you solve for it, pretty much you're going to find that C dot is equal to 105. Okay, great. So up here we have 105. Now why does that matter? We need to find the residue C. That is the difference between our extrapolated C and what we actually get. And as you can see in the equation that we have in our equation sheet, that's what this part is. This is extrapolated C minus the actual C is equal to the C residual. Okay, so that's just a simple subtraction. So we're going to do the C residual is equal to 105 minus 51.33. We're going to find that that's equal to 53.67. And so why do we need that? We need it for this equation. ln of C residual is equal to ln A minus KAT. Now, what does that mean? This is going to be our residual line. This is the line that goes from up here, crosses this line, this point on the actual curve. It goes out here. I apologize, this isn't straight, but it's supposed to be straight. This equation will use all the variables that we have in order to solve for Ka. So what are those variables? Well, C residual, as you know, is right here. A is 110, and T is going to be 0.25. So, putting it all together, Ln of 53.67 is equal to Ln 110 minus Ka. T is 0.25. And if you put that all together, you're going to get a Ka of 2.87. Now, as you can see in this equation, if this equation looks unfamiliar because it's not in the equation sheet, this is actually what this is. Remember, the C residual is equal to C extrapolated minus C. There's the minus KAT, and what you have to understand is this is A. This is your y-intercept. So, y-intercept is equal to F by, sorry, not minus, F times D times Ka over V. I apologize, I don't know why this is at A. That should be D, because it's the volume of distribution. Vd Ka minus K. This is your y-intercept. I had this equal to A. Now the reason this works is because both these lines have the same y-intercept. So in order to make up any line, you need to have 2 points. And we know this point because it's the y-intercept of this line, which are the same. And we know this point because it is on the actual curve, as we got from our graph. And so this is how you find the K and the Ka for question 1A. Okay, now moving on to question 1B. 1B is more of a contextual type of question. So the question is asking, can you assume that Ka is greater than K? I don't have a lot of space. I'm going to erase this. We don't need this anymore. So the question is, can you assume that Ka is greater than K? And the answer is yes, you can. In fact, you can assume that Ka is much greater than K. Why is that? Well, remember what K is related to. K is related, the elimination constant and the absorption constant is related to like time. So K is related to the half-life for elimination, and Ka is related to like the absorption half-life type thing. So if Ka is much greater than K, then what you're saying is that the time, let's just say the half-time for A is much less than the half-time for, or the half-life. And that makes sense because most drugs take a short amount of time to be absorbed than they do to be eliminated. You inject a IV bolus, it's going to be absorbed just like that, but it's going to take a while to be eliminated. Even drugs that you have to like take orally, it will take some time to be absorbed, but it's going to take a much greater time for it to be eliminated from the body. So most of the time you can assume that Ka is greater than K, or T 1/2 for absorption is much less than the T, the elimination half-life. Now, you can't, in order to make sure of that, which is the second part of the question, in order to make sure of that, you would have to either do two things. One, you would have to find a IV dose and compare this this K to this K. If it's parallel to this one, the elimination one, that means it's limited by its elimination. And if it's parallel to this one, it means it's limited by its absorption. And I'll get into that in a second. The other thing you could do is you could use the same drug but different formulation. So same route of administration. So for example, you could do sublingual versus oral in order to solve for it. So why is it elimination limiting if, let's say, our IV dose looks like that. Let's say this is IV dose, and this is by mouth. Why is the elimination limiting? Well, IV is only elimination, right? And so as you can, it's absorbed like almost instantly. That's what the whole point of an IV bolus is. You want to get it into the system right away. If it is parallel to K, that's just saying it's dependent on how long like this curve is dependent on its elimination, because IV only has elimination. If it were to look more like this, and sorry for all the lines, but what I'm trying to show is that it's parallel to this one. This is the absorption phase by the mouth. But if we had a IV dose that looks like this, as you can see, this is the absorption part, and it's dependent, or it's parallel to it, meaning it's the elimination of the IV is actually mostly based on the absorption, how long the absorption takes. So another way to put it is, in terms of all this, is that most drugs are absorbed very quickly, and then they take a while to be eliminated. The only reason they would be flip-flop, which is what they used in the PowerPoint, that it was flip-flop pharmacokinetics, is if you were to do like a different specialized dosage form, such as a delayed release or a sustained release. So you would have to manipulate it in order to get that flip-flop pharmacokinetics. But most of the time, this is going to be true. All right, so the last part of the question is asking you to find Tmax and Cmax. So that's right from your, the equation is right from your equation sheet. So Tmax is equal to ln Ka minus ln K over Ka minus K. Well, we have K, we have Ka, we solved for that. So it's literally just plugging it all in. We're going to find a Tmax of 1.02. And now we're going to find Cmax. So we have this equation, once again, in the equation sheet, Cmax is equal to F d Ka over V Ka minus K times e to the negative K Tmax minus e to the negative Ka Tmax. And it looks like a lot, right? But remember, this part is your y-intercept. This is A. So really, we could just get rid of all this and just put in A, the y-intercept. So we would get a Cmax equal to 110 times e to the negative 0.186 times 1.02 minus e to negative 2.87, 1.02. And you plug that all in, you're going to get a Cmax of 85.10. And how can you check to make sure? Well, you had a graph. They gave it to you. And as you can see, the numbers the concentration started to rise, and then they started to fall. I mean, that's just how it is, as you can see in the curve, right? So the highest point that we found on the graph is at time 1 hour, we had a concentration of 85.11, and as you can see, that's exactly what we got. At time 1 hour, Tmax, we got our Cmax, which was 85. And that's how you do 1A through 1C.